Okay, so last time we were looking at bilinear pairing, and we looked at how to find embedding degree. And so today we want to look at one of the applications of the embedding degree. How do we use it in real life? Or for what value is it? Of course, there are many other uses of this embedding degree, but today we're just looking at one of them. So we want to look at the notion of torsion groups. So the full torsion groups and the R torsion groups is what we'll be looking at today. Just to know what they are, what torsion groups are, and how to come up, if you're given an elliptic curve, how to come up with the torsion groups. So that's what we'll be looking at. So of course, I've said that full torsion groups in terms of the elliptic curves are just a set of points on the elliptic curves that have finite order. And so these points we shall call them torsion points. Now, so just a few terms to be able to understand what this means before we formally define it. Finite order, we mean that this is an order that we can count. For example, we can say it has order 4, it has order 5, it has order 6, or 1000, and so on, so that it's not of infinite order. So torsion groups are a group is just a set of points. It's a set of points. When we talk of a group, we're talking about a set of points. So that one we already know. And of course, this set of points should have the point at infinity, or the identity point. The identity point in terms of elliptic curves would be the point at infinity. And then should have the other points, the other groups points. In terms of elliptic curves, of course, elements of a group, members of a group will be points. So one of them will be a point at infinity, and then the other points. So this set is what we call a group, a set of points on the elliptic curve. Now, if this set of points consists of points that are finite order, then we shall call this group a torsion group. If all the points are finite order here, then we shall call it a torsion group. Of course, to make us understand this, we can proceed so that we'll get what that means. I've defined, of course, we already know the definition of an elliptic curve, and that I will just again define it. This is the short Weierstrass elliptic curve. And you see, for it to be an elliptic curve, it must be non-singular. That means that when you're looking at the points, this is the elliptic curve, supposing it's that. So we're saying that we do not have roots that are identical. So there are no identical roots. The roots are not identical for it to be, that is what we mean by non-singular when we say that the curve is non-singular. So it must be non-singular for it to be an elliptic curve. Now, so when do we say that this point is a torsion point? So a point P on the elliptic curve, of course, we've already talked of torsion points. So when do we say that this point P is a torsion point? Point P is torsion if this condition is satisfied. In other words, if you can obtain an integer if you can obtain an integer n such that n times p, in other words, if you add p n times, then you will find the identity. What that means is that the order of p is n. The order of p is n. So if you can get a point, all points that can be written in this form, all points on the elliptic curve that can be written in this form are called torsion points. So now if you are writing your code, and of course I'll be showing you how to write this code. If you're writing your code to give you the torsion points, then you're just giving the code this condition. Of course, you're telling the code, supposing that we are dealing with the field F5, and F5, assuming has 9 points, assuming F5 has 9 points, and assuming that one of the point is 2, 1, the other point is 4, 2, another point is 8, or let's say 1, 1. I'm just assuming, and of course there's a point of infinity, and all those points assuming that are there until there are 9 of them. Now, how am I writing my code in Rust? That will give me torsion points. How am I writing my code? Now, I know F5, we are dealing with the numbers 0, 1, 2, 3, and then 4. That is F5. The base is 5 here. So then I'm telling this code, I'm telling my code, first of all, obtain the points on this elliptic curve. The elliptic curve has 9 points. Obtain all these 9 points. After obtaining these 9 points, now give me points that fulfill this condition. Now, how does it give you these points? It checks all these values of the field, all these values of the field. So it multiplies all these values with each of the points and see whether this condition will be fulfilled. So for instance, it will multiply 1 by this, check whether the answer is infinite, the point at infinity, whether the answer is the identity point. If it's not, it will check this 2 with this point. So it does that for every point. So 2 with that, check whether the result will be identity point. If it's not, proceeds to 3, checks whether the result will be point at infinity. So it's doing 3, 1, 3 multiplied by that. And of course, we know how to do this. We've been doing it. For those who do not know, maybe we look at it again. Then it checks. Now, if it finds that 3 times this point is a point at identity point, then it means 2, 1 is a torsion point. It means 2, 1 is a torsion point. Now, it proceeds to the other point again, checks, multiplies that point with all these points and see whether I get a point at infinity. If you do not get a point at infinity, then it declares this one not torsion point. Then it proceeds to the next point and so on. So that is what the code will be doing. That's what the code will be doing. So it's moving through all these points and finding out which one, when multiplied by a scalar, gives you the point, the identity point, or the point at infinity. That's what we call the torsion point. That's what we call torsion point. Now, so I've explained what a torsion point is, and so what about full torsion group? Full torsion group. Now, so once you find all those torsion points, as we've explained above, all those torsion points would form a group. All those torsion points will form a group if you put all of them in curly brackets. And this group, therefore, is what we call the full torsion group of an elliptic curve. Now, of course, it depends on the field. I've talked of a finite field when f is 5 and when the base is 5. I've talked of that. Yeah. Now, so we could also have other fields. But of course, for us in cryptography and security, we are much interested in the finite field and not the other field. But of course, I just mentioned these other fields that we can also get to know how it works. But our point of interest mostly is the finite field, and that is how we will proceed to look at finite field. Of course, you can have complex field, you can have integers, and that is what I call number of a field over number fields. This will just be integers. You can find torsion group over complex numbers. You can find it over integers. Most our interest is on the finite fields. So that is how we proceed there. Now, so we talked of torsion. Now, last time we talked about the embedding degree when we introduced bilinear pairing. That was in the other lesson. Now, so that therefore brings us to the point of R torsion. R torsion here, we will first of all find the bilinear and then the embedding degree. And let me just remind you how we're getting the embedding degree. When we began looking at bilinear pairing, what we said the embedding degree was, it was the smallest integer k. So the smallest integer k is an embedding degree if you can find some r. If you can find some r, some integer r. And of course, this integer r, the integer r, we began by finding it. We found the integer r. Okay, let me remind what r was. What r was, first of all, we have the elliptic curve. And this elliptic curve, supposing has 9 points. And this is what the example we did. If it has 9 points, we ask ourselves, what are the divisors of 9? And the divisors of 9, therefore, is our r. The divisors, in this case, our divisor of 9 is 3. So 3 is our r. 3 is our r. So what is an embedding degree? As we did last time, we said embedding degree, therefore. Oh, and okay, just before that, what about q? Q is our prime number. Supposing the field is 5, the mod 5. Supposing the field, our field is mod 5. So our q will be 5. So how are we finding? So we found r is 3. Then 5k minus 1. So we were finding the smallest value k such that this expression will be divisible by 3. This expression will be divisible by 3. So for instance, if you take, what was our answer here? I'm just trying to recall the example we did. Our answer here, I think, was it 3 or what? The previous example. Because, no, it was, I think, 2. So that if we have 5 raised to 2 minus 1, this answer will be divisible by 3. this answer will be divisible because this is 25 minus 1, which is 24, and 24 is divisible by 3. So then the embedding degree becomes 2. I'm just recalling what we did in our previous example, in our last lesson. Now, so R is the divisor of the order of the group. If the group has 9 points, the order of that group is 9. And therefore, R is an integer that divides that order. Is what we call R. Now, so therefore, we come up with the R torsion group. R torsion group. So this in our case, R was 3 here. So we'll be talking about 3 torsion group, which we can also, over the elliptic curve E, we can abbreviate it as this. ER, or E3 in this case. This is the 3 torsion group. Now, how many elements will the full R torsion group have? The full R torsion group will have R square elements. And we've just seen that. In our case above, we had 9. So it will just be this 3 square, which is 9. We'll have R square elements. And then it will have subgroups. R plus 1 subgroups. So if R is 3, we'll be talking about 4 subgroups. 4 subgroups. Okay, we'll see how to find those subgroups. That's no problem. Now, but the most important thing here is how do we, the definition of a torsion group, a torsion point, we defined a torsion point, and now we come to R torsion group. And now what is R? We've already said R would be integers that divide the order of the group. The integers that divide the order of the group. Now, why do we study the full torsion groups? We are saying that they are important in elliptic curve cryptography, that is securing data using elliptic curve, and particularly the pairing-based cryptography, which I said last time that this pairing-based, up to now, it is still understood as, taken as one of the post-quantum secure cryptography. Up to now, it is still post-quantum secure. It's not like RSA. RSA is not post-quantum secure, but this pairing-based is post-quantum secure. Now, so the notion of the torsion groups, therefore, is important in this pairing-based cryptography. Now, what is the fundamental theorem of finite group? What does it say? And how relevant is it? Now, we want to look at the relevance of this, and it says that given any cyclic group G of order n, if you have a cyclic group G of order n, then every divisor R of n, every divisor of this order has a subgroup or defines a subgroup. Defines a subgroup. And that subgroup will be of order R. That is a subgroup. For instance, when you looked at an example last time that a group had 20 elements, we asked ourselves, the order of this group, our n is 20. Since our n is 20, we asked ourselves, what are the divisors of the prime factors? What are the prime factors of 20? And then we talked of 2 there, 10, 2 there, 5, then 5 here, 1. So we found that our R in this case will be 2 and 5. These are the prime factors that divide 20. So what we are then saying by this fundamental theorem is that every R that divides N would define a subgroup. So that means if your elliptic curve has 20 points, then we can find some subgroups, one generated by one because of R, which is 2. So R, which is 2, would have some subgroups, and this will also have some subgroup. The subgroup by 2, where R is 2, would have two elements. The order will be the same as R. And the subgroup where R is 5 would have 5 elements because the order of that subgroup should be the same as R. The subgroup should be the same as R. So I've just given an example. For instance, you have an elliptic curve, and this elliptic curve has 20 points. We are asking ourselves, what is R? And we found that if it has 20 points, then R will be 2 and 5. And of course, then this R, if R is 2, we can find it can give us a subgroup of 2 elements. So that subgroup of 2 elements is what we're calling 2, where 2 is R, 2 torsion group. And if R is 5, we are calling it 5 torsion group. And that 5 torsion group has 5 elements. Good. That is now where we want to do some examples. Let me just again remind what you mean by a torsion point. A point P is said to be torsion if you can find an R such that this R multiplied by P would give us the identity elements. So can we find R such that this R multiplied by P will give us identity elements for the point at infinity? Let's look at examples. And this example, I'll do it using Rust code. Of course, we can do it physically, but let's try and do it using Rust code. Now, you're given an elliptic curve E over a finite field with the order N. And this, of course, this is just still a definition of torsion. Then every divisor R of N defines a unique R torsion subgroup. It will give us a unique R torsion group of order R. This is just a repetition of what I've said above. And I'm giving an example of this elliptic curve. And this elliptic curve is y square is x cubed. Our A is 1 and our B is 1. So this elliptic curve and this elliptic curve is over F5. Is over F5. Now, how many points does this group have? This elliptic curve has. This elliptic curve has 9 points. And this is the order. So the only number that divides 9. Only prime number that divides 9 is 3. So in this case, our R is 3. So we can find a 3 torsion group, and it will have 3 elements. So, and those elements, I've found them here. So I'll use Rust code to show you how I found those elements. Let me just tell you what it means, because I've already said, but let me again repeat what it means. Our R is 3. So how do you find these elements? So we write our code, and our code is supposed to go through the elements here. The elements here are 9. The elements here are 9. So it's supposed to go through all those elements and see which one of them, when multiplied by 3, would give us the identity. It's supposed to go through all those elements and see which one of them, when multiplied by 3, would give us identity. So for instance, 3 times identity will just be the identity. What about 3 times 2, 1? And again, I found it will give us identity. What about 3 times 2, 4? Give us identity. But 3 times the other elements, you not get the identity. Now, if you're not doing using Rust code, of course, I'll show you how to use Rust code. And if you're not using Rust code, how are you doing this? How are you doing this? And we had already done this earlier. Let us again recall. I want to recall how to do this. 3 multiplied by 2, 1. This 2, 1 is a point. So what this means, this is the same as 3, 1 plus 3, 1, no, 2, 1 plus 2, 1. So this is how you do it without a code. And when you do this, when you add this, you get identity. First of all, you add this, and you know the formula of adding. You know that if you're adding 2 elements, this like points on okay, these are same points. These same points. So it's like getting 2p. When 2p is the same, we had our formulas for doing that. We had our formulas. So for getting gradient, or gradient S, we had our formula for getting the gradient. And then after getting the gradient, we would then find our x3 using some formula, and we get y3 using our formula. So then this point, this 2, 1, 2, 1, would give another point. Let's call it the value you find here. So let me say you find 2. Let me say you find 4. And let me say you find maybe 1. So you now come up with a point 4, 1. Come up with a point 4, 1. Now, so if this is a point 4, 1, now add 2, 1 to this. Now these two are now separate. They're different points. Again, for different points, we had a formula for getting the gradient, and then a formula for getting S3 and getting Y3. So when you do that, and of course, when you do this, you'll find that because it's supposed to give us identity, you'll find that the values, this points will be on the same vertical line. This point and that will be on the same vertical line. So for instance, this will be 2. But this will be different. This y value will be different, so that if you have x-axis and y-axis, these values will be on the same vertical line. So if they're on the same vertical line, then their sum is identity. If they're on the, like this point plus this point, the sum will be identity. Now, you recall our formulas, so you can try to do it manually. And of course, the example that I've used here is so smaller values. So it's supposed to give you, you can do that using the formulas we looked at for getting gradient if the points are different, and gradient if it's the same point. Now, so let me begin from here. Let me begin from, before I show you the code for doing that, let's begin from here and see how many points, no, here. See how many points this curve has. So I can share my Rust code just to show you that it's 1, 1, then 5. So I want to see how many points this one has. Okay, so this is my Rust code. It's very short. It's not a very long code. This is just for generating the points on the elliptic curve. This is my main function. It has A and B, and then the prime number. So my A was 1, my B was 1, and then the prime number is 5. So if I ask it to generate, so what am I telling it? I'm telling it to go through all the points of from 0 to P for the value of X. For X in this range, 0 to P. So it's going to P minus 1, 0 to P. So it understands that is P minus 1. Then I give it X cubed. That is X times X times X. So of course, I'm reducing it mod P and then reducing mod P, then reducing mod P so that the value is less than 5 at every point. The right-hand side is X cubed. I've already defined X cubed at this point. I've said let X cubed be this. So that now when I come here and I want to write, what do I want to write? What I want to write is y square. Y square is same as X cubed. This is normally our right-hand side, then plus checking where my plus sign is on my computer. Since I've not used it for some time, it's no problem. Then plus, supposed to be AX, then plus B. This is what I'm supposed to type. So this is how I type it. I've already defined what X cubed is here. It's X times X times X 3 times. So I come here, the right-hand side is X cubed, which is defined above, and then plus A multiplied by X. I want to reduce it so that it's less than 5, and then plus B, and then again reduce it. So that's what I wanted to do. So that is my right-hand side. My right-hand side is that. Then, so once I have the right-hand side, I want just to find the value of y. I want to find the value of y. So to find the value of y, I have the right-hand side. The right-hand side is equal to this. So the right-hand side already is y square. The right-hand side already is y square. So what I want is the square root of y. And the square root of y must be a value between 0 and 5. So I'm then telling it, for y in the range of 0 to 5, find a value whose square will be the same as y square. So I'm saying, for y in this range, find a value in this range. Find a value in this range such that y times y will give me the right-hand side, which I already have. The right-hand side is already defined. So give me a value that equals the right-hand side. So it's now going through, it tries 0, then it tries 1, then it tries 2, it tries 3, up to 4. Of course, when it reaches 4, it will have found a value that is whose square is equal to that. Once you find that, then print the point X and point Y. X was here, so X was here. So again checking. Then now it has found Y to print that. Now, if Y is not equal to 0, if Y is not equal to 0, then print this. If y is not equal to 0, we print this. X, then b minus 1. Now, so this is supposed to give me all the points. So it's supposed to give me all the points. Let me just run it. Yeah, so it has given me the points. It has told me that this code has 0.01, 0.04, 21, 24, 31, and so on. So it has all those points. And there are 9, these are 9 points. Now, so after I found these 9 points, I now want, as I had already said, I want to find out which of these points, when multiplied by 3, let me see, is it 3? Yes. Which of these points, when multiplied by 3, gives me point at infinity? Gives me point at infinity. Okay, so you can even have another code to do that. The one we had already looked at this code before, the code for scalar multiplication. So I had some 0.21. I want to see whether 21. Okay, my point is 21. I had some 0.21. This 21 I want to multiply by 3, n is 3. And my elliptic curve A was 1 and B was 1, but the mod was 5. So I want to see whether 3 multiplied by that point gives me point at infinity. So I run it. And when I run that, it tells me that 3p is a point at infinity. So 3p is a point at infinity. I can try another point and see whether it will be point at infinity also. 3,1. I don't know whether 3,1 was on that elliptic curve. I don't remember. But there was 0, there was 0,4. I remember there was some point 0,4 in the elliptic curve. 0,4. Let me multiply 0,4 by 3 and see whether to give a point at infinity. So 0,4 multiplied by 3 gives me 2,4. It does not give me a point at infinity. It does not give me a point at infinity. But let me check this 2,4. If this 2,4 is multiplied by 3, what will it give? This 2,4. What will it give me? Now the 2,4 multiplied by 3 gives me a point at infinity. Now, every point that is multiplied by 3, in this case, and the result is a point at infinity, we are calling it a torsion point. That's how we define it. We are calling it a torsion point. And the rest are not. So if all those torsion points are put together, they form a group. And this group will be called 3 torsion points. Will be called 3 torsion points because it is 3 that was multiplied by these points to give us point at infinity. Now, instead of having all these codes, I can just write one code to do this. I can write one code to do this. And this code, okay, let me run it. This code, I took a long time to write it. Okay, so let me just, before I run it, let me see whether I've entered the right values. Okay, so my A for the curve was 1, and my B was 1, and my mod was 5, and my R is 3. My R is 3. Now I want this code to give me all the points, which when multiplied by 3 gives me identity. All those points on this elliptic curve, mod M, which when multiplied by 3 gives me the identity. So I then run it. And it gives me that the first point is 2, 1, and we just saw it. We just saw that 2, 1 multiplied by 3 gave us the identity. The other point is 2, 4, and the other point is the point at infinity. So it has given us 3 points. So these 3 points put together, they give us 3 torsion group. Of course, I've just called it 3 torsion points on the curve. So these are the 3 torsion points on the curve. So these 3 torsion points, they give us the 3 torsion subgroup. Now, this code I have not explained how it works because I finished writing it very late. But we can just go through it. Can just go through it, and of course that is definition of the first part. So I'm interested in the functions. The function to implement a point at infinity. So function is at infinity. Is at infinity, then self-infinity, then function at infinity. These 2 functions are different. At infinity, these 2 functions are different. The first one is telling us whether a point is at infinity. Then this other one is now defining the infinity. It's defining the infinity. So what this one is telling me that if I multiply a point by 3 and get 0, 0, so infinity, you just define it yourself. I've just defined infinity as 0.00. 0.00, call it infinity. So if I multiply 3 by a number, then it gives me 0, 0. Then that is at infinity. Is at infinity. But this other function is telling me if a point is at infinity. If a point is at infinity. But this one is defining what infinity is. This one is defining what infinity is. I think you get the difference. The first one is telling me that the point is at infinity. What I've gotten is at infinity. But what is this infinity? The infinity is 0.00. So this is what this one is telling me. The infinity is 0.00. Now, so before even we go there, we have a function that we'll be getting the mod inverse, the inverse of a point, giving us the inverse of a point whenever it is required. So I say let t be mutable, and then also new t be mutable, and r be mutable, and then new r also be mutable. And so initially, we initialize t to be 0. Of course, mutable means it will be changing. So it's not static. The 0 will change to another number, and so on. And then the new t, we also initialize it at 1. And then, of course, we know how to get the mod inverse of 2 numbers. This is a and b, no, a and m. The inverse of a is a number which, when multiplied by a, gives us identity 1. But in this case, we are using the mod inverse. We'll be using the mod inverse. Now, so we also make new r be A. The remainder of M division by M. Now that is the initially just let T be 0, let mu T be 1, let R be M, and let mu R be M. Then, while R is not equal to 0, you enter this loop. While R is not equal to 0, you enter the loop. Inside the loop, you let the quotient be R divided by mu R. Then T be T minus quotient. The quotient will just be defined above, then multiplied by mu T. Of course, this one will be swapped. The mutable T will be swapped with the new T in the subsequent steps. And then R, you calculate R by the original R minus the quotient multiplied by the new R. And of course, again, the next steps, this will again be reversed. We swap with them, we swap, and so on as you proceed. Now, if R is greater than 1, then there will be a panic. If R is greater than 1, R is greater than 1, R is the remainder. You see, this is supposed to happen. The modular inverse is supposed to go until the remainder is 0. So when you find that the remainder is greater than 1, and you've done all the steps, then it means that there's no more, there's no inverse. There's no inverse. But if T is less than 0, that is, you have negative values, T is -3 or -4, then you would add M to it to get new T. So new T, the T, if T was -3 and your mod is 5, so what is T? T therefore is that -3 plus 5, which gives us 2. That is what this statement means. And so on. So you go through this. I have not written how the code works. But this code, we already looked at it, and this is elliptic curve. This is where we are doing addition. We are doing an addition. You have 2 points, P and Q. And this is the same thing I was explaining. If P is at infinity, and you want to add it to Q, if you're adding P and Q are the ones you're adding. So if P is a point at infinity, and you add it to Q, then the result will be Q. The result will be Q. Because infinity's identity is like 0. So 2 plus 0, we expect the answer to be 2. That's what it's saying here. If P is at infinity and you're adding it to Q, then the result will be Q. And if Q is at infinity and you're adding it to P, then the result will be P. That's what this means. The result will be P. Now, if Px equals to Qx, okay, that is point P and that is point, if they're equal, and if these two are equal, and Py, okay, let me just say, if you have a point, okay, let me talk of this. Let me just type it here so that you understand what I mean. Supposing my point P, I'm talking about point P. Supposing my point P is 2, 3. And let me suppose that my Q, let me just type this way. I think this way it's easier to understand. This one is 4, not 5. Now, what this one is saying is this. If the x value of P equals the x value of Q, and that's what I've just written, you can see the x value of p equals the x value of q. If that is the case, and if the y value of p is not equal to the y value of q, and you can see my y value here of p is not the same as the y value of q. If that is the case, then the y value, and if the y value of, this is just a continuation, this is a one condition, and if the y value of p is not equal to 0, no, is 0, if the y value of p is 0, so supposing the y value of p here is 0, supposing the y value of p is 0, now if you're adding these 2 points, if you're adding these 2 points, if you're adding these 2 points, the result will be the point at infinity. The result will be point at infinity. That's what it's saying. Like if I have 2, 0 plus 2, 5, the result will be point at infinity. We have defined our point at infinity above. We have defined it as 0, 0. The result will be a point at infinity. That's what this means, this condition. If the x value of p and the y value of p are equal, no, if the x value of p and the x value of q are equal, and if the y value of p is not equal to the y value of q, and supposing that the y value of p is 0, just any of them, whether y value of p or the y value of q, if one of them is 0, then the result will be point at infinity. Now, what about here? What if this is not the case? What if this is not the case? So if that is not the case, let's now assume that the x value of p is x1, and the y value of p is y1, and assume that the x value of q is x2, and the y value of q is y2. So these 2 points are different. These 2 points are different. If they're different, since they're different, you now find the gradient. And this gradient, I'll call it lambda. I'll call it lambda, the gradient. And let lambda, now we are defining how to get lambda. And there are 2 ways. If x value, x1 equals to x2, if these 2 values are equal, x1 and x2 are equal, and y1 and y2 are equal, then we are talking about the same point. We are talking about the same point. We're talking about the same point here. So that means, supposing I have this, and then suppose I have q as, suppose I have q as 2, 7. We're talking about the same point. If the x1 and x2 values are equal, and y1 and y2 values are equal, then we are talking about the same point. Then we do what we call doubling. Because it's the same point. It's the same point, we just double it. And to double it, you find there's what I've called a number here. I've defined it as number, num. I've defined it as num. Of course, it might be not necessarily the gradient, but the num, I've said let the num be, let the num be 3 multiplied by x1 square. And that is our formula we've been using, 3 multiplied by x1 square. And then you reduce it mod m. The num there is the numerator. Then the denominator, the denominator here, that is the numerator. And then the denominator, let the denominator denom be the mod inverse. The mod inverse of 2 multiplied by y1. Multiplied by y1. Of course, that is what you normally do. That is what you normally do. Then the numerator times the denominator. Okay, we will find the numerator times the denominator. Now, let me just show you what we normally do. What we normally do is the change in y over change in x. But for the same point, no, change in y, yes, change in y over change in x. But for the same point, we then use 3x squared plus a. I had forgotten a, 3x squared plus a. 3x squared plus a. Then over some denominator. Then that denominator, you will then find the inverse of it and multiply by the numerator. Now, that is the first condition. If x1 and x2 are equal and y1 and y2 are equal, that is the same point, so you double. But if that is not the case, then you go into else. That means x1 and x2 are not the same. And y1 and y2 are not the same. So if that is not the case, then how do you find the numerator? You change in y, then there will be the denominator, change in x. Change in x, but then you get the inverse of that. So that you multiply the numerator and the denominator. Now, once you have this lambda, the lambda here and the lambda there, you can get x3. x3 will be lambda square minus x1 minus x2, and y3 will be lambda multiplied by x1 minus x3, then minus y1. So then you can get a point. This is the point you get, x1, x3, y3, get that point. If the point is at infinity, then it will write false. Now that continues. Now, after it has calculated that point, we now want to ask it to multiply it by 3. Multiply by 3. At that point, multiply by 3 and see whether the result is at infinity. So that is what I'm now doing here. I multiply by a scalar. Multiply by a scalar. So I'll not explain this. You can follow that. Multiply by 3. So it has to find the point. After finding the point, multiply by 3. And see whether the result is at infinity. Now, then, if the result is at infinity, it means that point is a torsion point. Is a torsion point. So this is now what it finds a torsion point. This one finds a torsion point. So it goes through all those values 0 to m multiplying by that point and see whether it can get torsion point. Okay, that is how we write that code. So you look at that code later and understand how to write it. You can always try to modify it to suit what you want. You can add more content to it and so on. Now, so we talked about the R torsion. So what is full R torsion? We talked about the R torsion. R torsion, in this case, our 3 torsion, where 3 is our R. And just before that example, we had said that we have what you call the full R torsion, and this full R torsion would have R square elements, and it will have R plus 1 subgroups. So that notion is therefore what I'm now trying to explain. Once you have the R, our R, and you have the R, you have the R torsion points. What do we mean by the full R torsion? The full R torsion. I'll explain using the notion of three torsion. So these three torsion, we've already said will be all points which, when multiplied by 3 gives the identity. And our R in this case is 3. So you're saying that the full 3 torsion group would have 9 elements. And then we'll have 4 subgroups. It will have 4 subgroups. You know what is happening here? Our original group had 9 elements. So that is, of course, what we are saying. Then these 9 elements, if you arrange them into subgroups, you come up with 4 subgroups. You come up with the 4 subgroups. Okay, let's look at another example. That's another example. Now we look at this elliptic curve. Of course, we know what it means. We know that this means y squared is x cubed plus 8x plus 8. This one is done on F13. It's done on F13. Now, so first of all, before we find out the torsions, the torsion groups, we must first of all find out what are the embedding, not the embedding, but how many elements are here? We must first of all find out how many elements are here. So when you do it using the code we just did, you define it as 20 elements. And then these 20 elements, what are the divisors of this? What are the prime divisors? So the prime divisors are 2 and 5. So that means our R is 2, another R is 5. So this R2 can give us 2 torsion subgroups. Of course, they will have 2 elements. And the R5 will give us 5 torsion subgroup. And this 5 torsion subgroup will have 5 elements. So that is what I've just said here. That's what I've said here. Now, so the thing is, therefore, can you find the subgroup that the 2 torsion subgroup? Can you find the 2 torsion subgroup? So this one, again, you just use the code. When you use the code, you should be able to give you. Just use the code. If you have the code, it will just give you. Let me just see where the code is. Yeah, just the same code. So just change the values here. Our A in this case is 8. And our B is also 8. Our M was 13. And our R is 2. Our R is 2. So we want to find when R is 2, how many torsion elements would we have? How many torsion elements would we have? So then you find that we would have the point at infinity and the 0.40. 0.40. So those are only 2 elements. And that's what we said. When R is 2, you expect 2 elements. What about when R is 5? Expecting 5 elements. Which one are they? When R is 5, you're expecting 5 elements. Okay, one of the elements is the point at infinity, then 8, 8, 8, 5, 7, 11, and 7, 2. So what this means, if you take 7.2 multiplied by 5, or if you add it 5 times, give the identity. If you take 711, add it 5 times, get the identity, and so on. And so on. That's what it means by torsion points. Now, so the Rust implementation code that I put here is not the one for finding torsion elements. But it was just for proving that these are torsion elements. It's for proving that these are torsion elements. So what I did was, the one that I've added here is the one for scalar multiplication. So I'm taking, for instance, 7.2, multiplying by 5, and I want to see whether it gives me the identity. So that's these are different. It's a different code. It is for scalar multiplication. So it's the one I'm looking for, scalar multiplication. So for instance, I'm taking that 0.72. There was 0.72 there. 0.72. What is n? N is 5. And my A is 8. My B is 8. And my mod is 13. So I want to see 7.2 added 5 times. What will be the result? Will it be the point at infinity? So just to verify, just trying, I'm using this to verify. And yes, 5p is a point at infinity. So this code here is just for scalar multiplication. Of course, the way these codes are is just the same way you write. You can see the same thing. We began by this in the previous code. Began by this, and then followed by what is a point at infinity. We defined a point at infinity. Then came to mod inverse. So they're doing the same thing. They're doing the same thing actually. And the same code. You can see in this one. The same code, same function, same function. So we just vary a few things. That's why I say once you know how to write one code, always write the other one. Or once you get used to writing this, you can always customize. Like when I was writing that for torsion, I tried to write it in the other way. It was not very easy. So I had to take this one and customize. I just took this and customized it. Made a few changes and it gave me the result. But that was very late after I tried so many tactics and it was not working. So then when I thought of, let me customize this, and it works. So you can see the same thing. We'll vary very few things, and you have it. Like we just want to multiply by a scalar. So in fact, we can just do the same code, but now I ask it to print something different. Ask it to print if a point is print for me n times p. Okay, if it's a point at infinity, it will tell me that that's a point at infinity. So is that just the same codes? The same codes. Okay, let me just show you that it's the same code so that you can see that you can always, once you have one code, you can always think of, can I use this code to come up with the other one? And you see how to customize. You can see this. This is the same code I was explaining, just the same as the one I was explaining, although it's not the exact one. They're the same. Let me now show you the one that was doing torsion. And you see that they're not different. They're not different. The one that was doing torsion is this. Let me show you that it's the one that was doing torsion. This one, when you ask it to, when you run it, it gives you the elements. But the one that I've just been showing you, it gives you whether the elements are at infinity, only that. But this one gives you all the elements of that, or the torsion elements. But look at it from the top. Just look at it from the top to see that it's just the same thing. Yeah, it's the same thing. Then you come here, mod inverse, the same thing in the same way we do mod inverse. Can never be different. And then if you are doing summation of points, again, it can never be different. The formulas for summing points, whether it's if it's the same point, you're just doubling. And the formula is the same. And then now scalar multiplication. And so this is the only place that I did make some changes, some slight changes because of the result that I wanted. Then I added this find torsion. I added this find torsion. Oh, this one I also added is on curve. If P is at infinity, return true. But the rest are just the same thing. The rest are just the same thing. So once you have one code, it's always easy to use it to come up with the other code. If they are related, that is. Now this code I've added the explanation of how it's used. So at your own time, you look at how it's used. But of course, it's the same explanation I'd given. Because it's just the same code. Most of the things are the same. I had already said that initially initialize t to be 0 and so on. Then you will compute the quotient. This is how you will compute it. R divided by the new R and so on. So this is the explanation for the modular inverse, then the explanation for point addition, and so on. So that's how you do it. That's a point that is about a full torsion point. The good thing, we now know what a torsion point is and how to find the subgroups. And now we'll see how then do we use these torsion points going forward, especially in pairing. Because we said the knowledge of this is very vital in pairing. So we want to see how vital is it, where is it used. Of course, in our last lesson, we saw the embedding degree and we have seen how it's important here. We also see how, in which other areas do we use embedding degree. So you go look at this for the torsion thing we learned, so that when we continue with our pairing-based cryptography, and of course we'll be looking at even signatures, how to do signatures using pairing, bilinear pairing, and so on. So this notion of torsion and embedding will still be recurring, will still required. Thank you. I wish to stop there. Cecilia, are you the one?
Yeah, we can end there.